In the rapidly evolving world of software development, performance isn't just a luxury, it's a necessity. From high-frequency trading platforms to real-time gaming engines, microseconds can mean the difference between success and failure. What secrets lie behind the speediest programming languages, and how do they push the boundaries of computational efficiency? C and C++ reign supreme in the performance arena, consistently demonstrating why they remain the go-to languages for system-level programming and performance-critical applications. Consider the case of the Chromium web browser, which leverages C++ to achieve blazing fast rendering speeds. The language's direct memory manipulation, low-level hardware access, and minimal routine overhead allows developers to extract maximum performance from hardware. Benchmark tests regularly show C++ outperforming interpreted languages by factors of 10 to 50x, making it a weapon of choice for performance engineers at companies like Google, Microsoft, and Apple. Comment below what's the most impressive C++ performance optimization you've seen. Rust emerges as a modern contender, challenging traditional performance paradigms with its unique combination of safety and speed. Unlike C++, Rust provides memory safety guarantees without sacrificing performance, achieving near-native execution speeds while preventing common programming errors like null or dangling pointer references. The Mozilla Firefox Quantum browser rewrote significant portions of its rendering engine in Rust, experiencing substantial performance improvements and reduced memory consumption. Compiler optimizations and zero-cost abstractions allow Rust to compile to highly efficient machine code, making it increasingly attractive for systems programming, blockchain technologies, and high-performance computing. Let's dive deeper into the technical nuances that differentiate high-performance languages. Compilation strategy plays a crucial role. Languages that compile directly to machine code like Go, Rust, and C++ naturally outperform interpreted languages. Just-in-time JIT compilation in languages like Java and JavaScript provides a middle ground, dynamically optimizing code during runtime. The Java Hotspot VM, for instance, can achieve performance nearly comparable to C++ for certain workloads through aggressive runtime optimizations. But can a JIT-compiled language ever truly match the raw performance of a statically compiled language? Performance isn't just about raw speed, it's about efficiency across different computational domains. WebAssembly (WASM) represents a groundbreaking approach, allowing languages like Rust and C++ to compile into a compact, high-performance binary format that runs at near-native speeds in web browsers. This technology has revolutionized web applications, enabling complex computational tasks like video editing, 3D rendering, and machine learning directly in the browser. Languages optimized for WebAssembly can achieve execution speeds up to 80% of native code, bridging the performance gap between web and desktop applications. The future of high-performance programming languages looks incredibly promising. Emerging languages like Julia are specifically designed for scientific computing and numerical analysis, offering performance comparable to C while providing more developer-friendly syntax. Parallel processing capabilities, GPU acceleration, and advanced compiler techniques continue to push the boundaries of what's possible. As hardware becomes more complex and distributed computing more prevalent, programming languages will need to evolve, providing developers with tools that can harness incredible computational power efficiently. What language do you think will dominate high-performance computing in the next decade? Drop your predictions below. Please like and subscribe for more content like this. Also, comment down below if you have insights to share.